Aerospace Ground Bond Testing. Today's webinar is brought to you by Designworld and TGM. So, it's 2 o'clock Eastern Time, so people are starting to kind of log on here. So before we get to the actual presentation, I'll go through here and mention a few housekeeping points of order. Just want to let everyone know here that this webinar will be at our website, designworldonline.com, after today's webinar, if you'd like to view it or reference it once again. And everyone who registered will also receive a copy of the webinar via email. There's a resource widget at the bottom there that you can use to view the webinar slides. You can move them around and size them to suit your preferences. Also, if you're watching this on demand, you can still interact with the presenters. You can submit your questions via the Q&A widget at the bottom of the console, or contact them directly via email. At the end of the webinar, though, we will have a Q&A session. So if you have questions, we would say go ahead and enter those, and we will try to get to as many of the questions as we can. Also, if you're on Twitter at all, you can tweet about the webinar using the hashtag DWWebinar. So, my name is Miles Budemer, and I'm a senior editor with Designworld, and I'll be moderating today's webinar. And now, a little about our presenter, Adam Flater. So Adam is president of TGAM. He holds a BSET degree from the University of Akron. Go Zips, I have to say. As well as an MBA from Case Western Reserve University. He's been with TGAM for 15 years, serving also as Director of Marketing and Sales. And he has over 20 years of experience across broadcast TV, airborne radar, and industrial automation. So with that, I'll hand it over to you, Adam. I hope I did a good job with your bio there.
Just fine, Miles. Thanks so much. And for the last 15 years at TGM, I've been really spending a lot of time with aerospace companies on test equipment. And the topic of aerospace bonding and grounding is one that I've become familiar with. And so it's going to be the obviously what we're focusing on today. Any really discussion of grounding and bonding in an aircraft covers a wide range of subjects and engineering disciplines, and we can't cover them all in depth. Hopefully what I'm going to give you is some of the basic tools and understanding and ways to research and do some more. So first thing that we're going to do is define some of the terms that I use and some of the methods, so that when I refer to them during the presentation, that you'll have some grounding in what I'm talking about. First, we'll look at mechanical bonds. These are actual, mechanical structural bonds that can be tested electrically, and we'll do those for clarification and thoroughness. Then we'll start looking at the classes of electrical bonds. First will be Class A for antennas. Class C will be current path bonds. Class H, shock hazard bonds. Class R will be electromagnetic interference bonds. Class L, lightning bonds. And finally, the Class S, the static discharge bonds. And then at the end, I'll give you some of the standards and resources I've referenced during this presentation, so that you could, again, do more investigation on your own. Okay, definitions. Ground. This is really a conducting connection, whether intentional or accidental, by which electric current can return to the ground reference point, usually the Earth, but in the case of an aircraft, it's actually a structural, relative location in the plane itself. A ground plane is a surface with many ground points on it that are usually assumed to be equal potential. So they're all theoretically zero. We'll find out that in certain occurrences that assumption is bad, but it's still necessary for general operation. Then a ground bond is actually the physical connection, the way that ground is connected to the ground plane. So here are some general test methods that are used. The first and obvious one is just use DC resistance. You take a digital multimeter, you measure ground, you measure the resistance to ground. Unfortunately, when you're measuring grounds, the values are usually quite small, and a DMM doesn't have that resolution. And often the leads of a DMM are more than the thing you're trying to measure. So for that reason, 4-wire measurement is preferred, and this is a standard DC resistance measurement with 4-wire will give you an answer. But what will occur is many of the grounds in an aircraft will go through dissimilar metals. So you might have copper connecting to aluminum, you'll have titanium, you'll have even steel at times. So these dissimilar metals create thermocouple joints effectively that have thermodynamic voltages associated with them, and these will really interfere with the standard DC measurement. And so the waveform on the lower right corner is a DC reversal waveform, and what you end up with is passing a current through one direction, measure the voltage drop, reverse that, measure the voltage drop again, and come up with a mathematical average to take out the effect of the thermocouple potentials that may interfere with your reading. They don't reverse potential in that case, so you're able to exclude them. And an older technique is the AC resistance, and this was used because the AC waveform, of course, reverses polarity and does cancel out some of the thermoelectric effects. But these are older instruments. You'll still encounter them, but they're not actively produced at this point. The DC reversal method, of course, accomplishes the same thing with higher accuracy. You'll also see what's called an AC loop tester. This uses the AC waveform, but it'll use some transformers to couple in and monitor the resulting current flow. So these are non-contact measurements, so they're quite useful in certain circumstances. And then finally, I list ultrasonic here for thoroughness, but also to alleviate some confusion. You will find that there are some mechanical tests performed with ultrasonic testers that aren't electrical bonds, but they're called bond testers. And what they're looking for is adhesion bonds or mechanical bonds. And we'll look at that briefly when we get to that point. So first, mechanical bonds. Even though there are a lot of aircraft designed with composite structures, the primary method still is aluminum structures. So you actually have sheets of aluminum riveted to an aluminum structure underneath. The aluminum, of course, is a great conductor. However, was exposed to air and oxygen, it begins to oxidize. And aluminum oxide is an insulator. The obviously tight rivets and joints are essential for structural integrity. And what occurs when a rivet is first installed into a piece of aluminum, it's a very tight joint, and it actually excludes the air. It's an airtight joint, so it doesn't oxidize. It has a very low resistance path, and with an instrument you can measure from a rivet to the aluminum skin and come up with a resistance. Now, when a rivet is tight and properly installed, you'll have a resistance that's substantially below 2.5 milli-ohms. But of course, what happens is an aircraft, it goes to altitude, it gets cold, it goes back to ground level, it warms back up, it sees a lot of temperature cycling, wings flex, things move in flight. This will tend to cause a rivet to actually loosen. And as it does, it allows the air to infiltrate underneath, and aluminum oxide can start to form. As this grows, this annulus of aluminum oxide grows and gets under more of the rivet head, the resistance goes up because, again, the aluminum oxide is an insulator. So as that occurs, it'll exceed the 2.5 milliohm limit, and now you can start to say, this rivet's actually getting loose. The preferred method here would be a DC reversal. Again, it's going to be a low value, and the aluminum skin and the rivet are both readily accessible with a set of probes. The next type of aircraft structure course is now the composites. The diagram on the right is really a stack up of the carbon fiber composites at the base with some fiberglass, some metal mesh in there for conducting away electrical events, and also creates a ground plane. And what can happen is, this is the mechanical bond that's an ultrasonic. It's looking for a void or a delamination in this stack up. And again, that's called a bond test. And if you Google bond testers, you'll find those come up as well. But they're not to be confused with making an electrical measurement. To further confuse things, you can make an electrical bond test to this also, because the metal mesh, which is acting as a shield, things will get grounded to it, things will get attached to it, and you'll need to make that test with in this case, a DC reversal method is preferred. Again, low resistances, and you have to get on some physical points. So now we begin looking at the first of the classical electrical bonds, Class A and antenna bond. There are a lot of different antennas on an aircraft, of course. One of them is a common one, the quarter monopole radiating element. You basically have a radiating element that's a quarter wavelength high, and part of that structure then will include what's called a counterpoise for an antenna. And obviously antenna design is beyond the scope of this webinar, but suffice it to say that the ground plane beneath the antenna is important for coupling as much energy as possible to the atmosphere. So if the ground plane is not formed sufficiently, or of course, if it's designed incorrectly, it'll have high reflection. But if the antenna becomes separated from the ground plane, you also have high reflection. This, of course, reduces the antenna range. And so it's important to actually test how the antenna base is coupled to the ground plane itself. This, of course, is a picture of a Predator drone, but if you see on the back, the shark fin, that's actually a quarter monopole antenna on the back of it, and the counterpoise is built right into the structure of the aircraft on the back. This is typically measured at DC. Again, the limit of 2.5 milliohms is telling you that this is well connected to the ground plane. However, that's not really the impedance that appears at the RF frequencies that the antenna is operating at. RF ground is quite different, and we'll actually look at that later on. But something that comes into play here is also just how your probe is designed. A lot of probes are 4-wire probes, so I have 2 conductors in each probe, and they may not be sufficiently. That may be too large to actually get into some of the mounting bolts and things around an antenna. And so sometimes you need to use a coaxial probe that has a center conductor with an outer conductor to get into tighter spaces. And due to the nature of these structures and the low level of resistance you're measuring, and the DC reversal method works quite well here. The Class C is all about the current path return for power sources. So in an aircraft, there are a number of different power sources that are used. 28 volts is the classic one, 115 volts, 400 hertz, 230 volts, variable frequency exists. And on the F-35, they're actually been applying a new 270 volt DC bus. And the concern here is that if the return conductor is not sufficient, that you have a fire or arc hazard problem. And of course, that's designed correctly at the beginning, but over time, these things can, connections can loosen and things can degrade. So this has to be verified periodically. And the loads in an aircraft can be rather large. There are flight surface controls, fuel pumps, air conditioning, wing de-ice. Wing de-ice is an enormous load, one of the largest loads on an aircraft. And so if the conductors are not sufficiently connected, again, you could get a hot spot, so you could generate a fire problem, or even in the case of a fault, if the resistance is too high, a breaker may not trip to isolate a system. So a number of things can obviously go wrong. The actual resistance that you're measuring depends on the potential fault current. So the chart on the right shows the blue trace is the maximum resistance for a given potential fault current. So you can see at 100 amp fault, the desired resistance is to less than a milli-ohm, about 950 microohms, and that varies again with the type of load. And this is taken from the SAE ARP 1870. There's a chart in there, both a table of fault currents and maximum resistances for them. The orange trace is what's considered to be the hazard level. The blue trace is approximately 20% of that. So things that can come into play here, of course, aircraft has aluminum conductors, how these are terminated. Those can, again, as we talked about aluminum oxide, those can corrode. They have to be checked periodically. The failure modes, if a current path doesn't come back to the right path, it can generate an arc somewhere, igniting fuel. Equipment might not function because it doesn't get sufficient supply. And again, breaker might not trip on a fault when it needs to. Due to the nature of the conductors, DC reversal method, again, you need to be able to accurately measure very low resistances properly, and you'll also need to check open runs. So you'll have a conductor that comes back from a load somewhere. Of course, you have to disconnect part of that load to check that, and the DC reversal method is preferred for that. Similarly related is the Class H. Again, it relates to some of the power conductors in an aircraft, but the concern here is not a fire hazard, but it is a shock hazard. So if you have a fault on a circuit breaker, of course they're built to tolerate some overcurrent without tripping, but the intent is that this could apply some hazardous voltage to, say, an instrument case, an instrument panel, maybe avionics bay somewhere. It's considered bad form to electrocute pilots during flight. So what the goal here is to produce a solid ground on an enclosure that may be exposed to a person, and so something like 5 times the rating of a breaker, so that it would trip and clear very quickly. Again, the SAE ARP 1870 contains actually Table 1, which is a whole list of resistances based on the type of equipment and what the potential fault currents could be available. There's just a few of them listed here, but the goal is to not expose personnel to something over 4.5 volts. That's a very conservative rating. Many industrial safety standards expose you to voltages as high as 50 or 60 volts, considering that to be safe. But out of an abundance of caution, the goal is to have much lower voltages in case something goes wrong. Again, you got some headroom. So the chart on the right, the orange line is really just a plot of the voltage drop against the potential fault current. So at a 1,000 amps fault current, you could see obviously 10 volts. But if that were a higher resistance, a tenth of an ohm, you can see that would expose someone to something as much as 100 volts. On an enclosure, there are, of course, safety standards, but there are also EMI standards. And so in some cases, the EMI standard may reduce the actual resistance that you're permitted to get away with. Instead of a tenth of an ohm, in this case, 2.5 milliohms. Again, an indication of a good solid mechanical connection. A couple of test methods that are applicable are obviously the DC reversal method. Some of these values are fairly low. You can get onto a cabinet and start points of a ground quite easily. But if you have multiple ground connections in a cabinet, you may be able to use the AC loop tester, and also that could be used on potential RF shields in there as well. So now let's talk about RF shielding. Class R bonds are used to be called RF bonds. Now we call them electromagnetic interference. A good reference for this is MIL Standard 464. This comes a lot from section 85.10. The 464 covers a wider range of electromagnetic topics, but grounding and bonding are critical to the operation. A couple of terms here. EMC is electromagnetic compatibility, and EMI is electromagnetic interference. Compatibility is what you're radiating, and interference is what you're susceptible to, from the perspective of an instrument. If you're having bizarre behavior in an aircraft, one of the first things to check is the EMI bonds, because when those are not functioning properly, many things can go wrong. Aircrafts are exposed to a wide range of frequencies, 30 megahertz to 30 gigahertz, even beyond that now. Radar systems, the radars of other aircraft or sources, ground radars at the airports, communication links, the satellite links, mobile phones, lightning, even solar emissions. So there are a number of things that can cause electromagnetic interference. What's one thing to be aware of is many of these tests are performed at very low frequencies to check a bond. So the standard specification, again, 2.5 milliohms for a shield bond, but that's measured at DC. And I see actually I have a typo here. I'm missing the word not. So this limit has not been determined empirically. This has been determined to be effective over time. But what this plot is on the right is this is a 350 MCM cable, so a very, very large conductor, like a piece of welding cable, 1 inch long. At DC, it's about a 2 microohm short. Well, you can see it as the frequency increases, even at a megahertz. That is a resistance of an impedance of nearly 50 milliohms, and as you can see at 10 megahertz, that is increased to nearly half an ohm impedance. So the behavior at RF frequencies can change significantly. One thing to note here about these tests is the standards prefer low currents and low voltages to make these tests, because shields don't typically see high voltages or high currents, they're draining fairly low amounts of energy. And so if you hit that with a very high current or a large voltage, you can punch through oxides. You can actually distort the measurement that you want to take. So keeping the currents and voltages low during this test is a better test of the real world performance of this bond. If a bond is not working correctly, if there's something wrong, the failure effects that can be innumerable. Sensors can be read incorrectly, or readings be interfering with instruments. Communications can be garbled, both voice communications and even digital communications on control buses. You'll get a false positive indication of different faults, misactivation of controls. They don't operate smoothly. They don't operate on command. And of course, one of the scary ones is the ordnance activation. I'm told it's really bad to detonate missiles and bombs while they're still attached to the aircraft. I've never experienced that myself, of course. And the shielding, you look at the picture on the right here, there are various hatches and doors that open on an aircraft, and there are shield interfaces at these points. And this can degrade over time just through oxidization, through wear. They can get coated with, paints, overspray, or even just mechanically distorted by people working around them. And so they need to be verified that they're still operating correctly. The methods for testing, again, DC reversal works well, low levels. You get 2 probes on several points, but also the AC loop testers can be very useful here. A lot of cabling has overshield on it, and you may not be able to get onto the shielding easily with a set of probes, and the loop testers allow you to clamp over the cabling and detect a good ground. So they can be quite handy in this application. Now, one of the most exciting classes of bond is the Class L lightning protection. It takes a lot of the worst cases of all the other bonds and rolls them all into one case here. So lightning is certainly very dangerous on an aircraft. It can see 200,000 amps of current flowing through the body of an aircraft. And because it has such a fast rise time, it includes an RF component that's significant. So the things that look to be very dead shorts at DC can now start to have significant impedances as the frequencies go up. And the design of how to construct a bond so that it operates better at RF frequencies is beyond the scope of this discussion. But if you refer to some of the standards, there's some good discussions on how to do that. As a quick example, 200,000 amps of DC flowing through 2.5 milli-ohms is still 500 volts, even without the increased impedance caused by the RF. What happens when lightning enters an aircraft? It's typically entering at the front of an aircraft. Lightning strikes are more common in climbing out or as in descent because of the altitude. The operational altitude of a lot of commercial airliners, of course, is way above the cloud ceiling. So you're usually moving through, again, an ascent or a descent. And of course, you're moving through space as you encounter a voltage gradient in the atmosphere. It's most likely the front end of the aircraft is going to see it first. So as this current is flowing through the airframe, though, it has to be directed around the, fuel systems, around electronics, around a lot of systems that are going to be sensitive to this enormous impulse. And the bonds have to be secure to do that. If your bonds aren't properly designed and in proper working order, the lightning can take almost unpredictable paths. And as you can see from the one small picture there, this is This is a bond after a lightning strike. It's fused and welded. A bond may no longer be suitable for protection, but it still may read very low because of the size of the bond itself. It may still have a lot of metal in contact, but be weakened. So visual inspection is also a part of seeing what has happened to an aircraft after a significant lightning strike. And here with these very low resistances that you're measuring, often DC reversal is a good method. More sensitive at the lower end. AC loop testers are not as accurate at the low end where a DC reversal instrument is. And finally, we come to the one of the more unusual classes, the Class S static electricity bond. These can vary quite a bit depending on the need for bleeding off static electricity. It's usually slower. Static comes from a number of sources. It can come from just precipitation, rain, snow, sleet. As that courses over a wing, it can transfer charge to the aircraft. The same is true of really just the air or dust in the air. Passing through a charged cloud can also couple charge to an aircraft. And beyond the atmosphere coupling to a charge to an aircraft, you can also get this happening inside an aircraft in some of the fluid lines. So if you have hydraulic or fuel flowing inside piping, this can also create buildup static. So the piping needs to be grounded as well. I'll give you an example. So the human body can store conservatively 25 millijoules of energy. If you look on the right, the formula for energy storage is U equals 1/2 CV squared. And it only takes a quarter of a millijoule or 250 microjoules to ignite fuel vapor. So to give you some idea, it's really only 71 volts on a 0.1 microfarad capacitor is enough to ignite fuel. So, controlling this static, not letting it build up on areas is very important on an aircraft. And so you might have, plastic components or various things that are interconnected just to drain this charge off. And typically these bonds can be fairly low. However, in some cases, you don't want the charge to discharge rapidly. This is an example when you're fueling an aircraft. They actually plug in a ground strap, and the ground strap has several thousand ohms of resistance in it just so that it doesn't generate a spark when you plug it in. You want to drain that slowly. And for the different type, the very nature of these bonds, DC reversal method, again, it's a very effective way to make this measurement accurately and quickly. So with that, I'm to the final slide here. If you're getting ready with your questions, the standards I referenced a few points in here and used for this presentation. The one I recommend first and foremost is the SAE ARP, that's Aerospace Recommended Practices 1870. That covers all of these topics well and goes into a lot of depth on mechanical construction of bonds even. The MIL Standard 464 is also another great reference. It's focused on the EMI primarily, so the interference and why bonding is important there, but it does touch on some of the others. It also has some nice sections about lessons learned. And both 1870 and 464 also reference other specifications. So they're good places to start, and then you can see other specs that are called out for different applications. And another document it's somewhat out of date as maybe as a reference tool, but it's still good background reading, is a NASA publication called Electrical Bonding, a Survey of Requirements, Methods, and Specifications. And you can find that on the nasa.gov website. And it has a little more examples of some things and also lessons learned that are useful. So again, if you're interested in going further, the 1870 and Mill Standard 464 reference other specifications that are useful. So with that, that concludes my portion, and I guess I'm ready to do some of the questions now.